All right, hello, and welcome to part two here, where we will be simulating what we solved for part one here in Python. So I have already done our imports here, and obviously the most important one, the most essential one, is this solve IVP, which we'll be needing to even simulate it, right? So I have uh, screenshotted the paper that I wrote on earlier, and I have all our stuff here. So, what should we do first? Well, we should put in our initial values, right? And I will be sort of assigning them all at once here in one line. Those were 0.5, 1, and 2. I will also be assigning the cross-sectional areas all at once here. Well, not all at once, I guess I should say in one line to be more accurate. They also had the same values here. What other initial values do we have? Let's see. Our alpha values, which I will simply just type out as alpha 1, 2, alpha 2, 3, and alpha 3. And those were all 0.1. We also have our set point for the height of the fluid in tank 3, right? Which we'll be needing for our control. And that will be set to 4 meters. And we also have our proportionality constant for that control, which is also set as 0.1. All right, and I'll shift into that. Now, before we move on to the next step here, let's think a little bit. So I have new solve IVP a little bit before making this video, so I can say that from SciPy and whatever method solver that we use, they all want the function that you put into it so that it can run through whatever it does to solve it for you. They all want it in different formats, and that doesn't exclude solve IVP from that sort of requirement. And so solve IVP wants our function in a specific format for it to work. So let me start defining a function here, and I'll just label it diff for differential. And so the way it wants it are the arguments, at least. They want our independent variable to go first. And in this case, since it's a simulation, it'll be time. And in most cases, for all differential equations, it's always time. And they want our dependents to be brought in via vector. And so what are our dependents, right? So it's our heights, because as we discussed earlier, since the cross-sectional areas are constant, the only things that are changing, with time at least, are heights. So what we'll be unpacking from that vector is the heights. All right. So what does this function need? Well, it's our differentials, right? It'll be returning our right-hand sides of our differentials. And just as a note, we will have to divide by the cross-sectional areas to have a proper right-hand side, right? So in any way, we'll need our flows, all our equations for the flow in and outs of all the tanks here. So let's start off by putting those in. So Q12 will equal np.sine here of h1 minus the height of 1, the tank 1 minus the height of tank 2 times the alpha value from tank 1 to 2. And this is also being multiplied by the absolute value of height 1, tank height 1, height of tank 2, all raised to the half power, which is a square root. And since the flow of 2 to 3 has a very similar equation, I can copy and paste that to make it quicker and change the values in here to their appropriate values. forget that. All right, and the flow of Q3 is simply the general equation for that. And so that will be alpha 3 times the height of 3 raised to the half power. All right, so now that we have those set up, we also need our control, right? We have a controller set up for this, these tank dynamics, right? Sorry if you can hear anything in the background. So Q in, the flow rate going in to tank 2 here, we'll have this proportionality constant, and that will be the difference between the set point and the actual fluid height within tank 3. All right, so let's return our differentials now that we have everything set up. So it was negative Q12 divided by, remember we gotta, to actually have it as a proper right-hand side, we need to move that constant cross-sectional area over. I forgot my bracket here. Then it was Q12 plus the flow rate in minus the flow rate out. Almost forgot to divide by the cross-sectional area there. And then we have our third tank, which is Q23 minus Q3. That's divided by the cross-sectional area. All right. And that is it for our function portion. So let's put it into solve IVP here. So, oops, IVP. So it wants our function, which in this case is just diff. And so now it wants the time span. It wants how to know how long the simulation is running for, right? And in our case, let's say I wanted to adjust the simulation in the future. I could have our end time for the simulation be its own variable. So I can just adjust this variable. Instead of going in to the actual solve IVP, IVP and messing with that. And so let's say I want it for 50 seconds. So I'll put that in. And now it wants our initial guesses, which our initial guesses are just our initial parameters, which is the initial heights, right? The things that are actually changing. So I will put those in. And the initial height of 13. All right, now it wants the method, which will be, I will be using Radau. And if you want more insight on that, all I can tell you is that it's an implicit method, very accurate, very stable, but very slow. It's way better than Euler's, which is an explicit method. If you want more on that, I'd recommend just searching it up on Wikipedia or something. As far as things that I know, that's basically all I can give you. So, moving on, we have this dense output that we can put in here, which we will be using. And for now, I will be setting it to true, and I will explain why in a bit. So let's run this. I have something wrong here. That should be right. Oh, I see the problem. All right, I forgot to put my multiply sign there. All right, now it should work. And now we have all this stuff from solve IVP. These T events here, or well, more specifically, this Y here, is our heights. And as you can see, there's 3 arrays for these 3 different tanks, right? And well, that's the values we need to plot our simulation, right? Well, not quite. As you can see with our time array, the step sizes are not consistent. They are all over the place, some being very small, like 0.08, and then this jumping up by 7. And that's just a sort of an artifact of using the Radu method, or solve IVP even. They sort of calculate the step sizes themselves to minimize the error, which all in all is a good thing. But it calls for something that we'd be aware of so that we can work around it for our simulation. And so because of that, we need to sort of create our own time variable for plotting purposes, one that is consistent. Because if we do plot it the way it is now, our simulation wouldn't look good. It would be jagged, sharp, right? And if we wanted intermediate values, they wouldn't be correct. And so, like I said earlier, we need our own time variable for plotting purposes. But there's another issue with that. In order to use a time variable for plotting purposes, we need a function to pass those time values through. And as of right now, where is that? And that's where the dense output being set to true comes to play, like I said earlier. If this dense output were false, I will showcase that now. As you can see earlier, the thing that changed was this sol sort of value. It's now set to none. Well, that sol is basically short for solution. And in terms of solution, it actually gives us a function to use to sort of, like I said, insert values and get a proper value back for the heights of tanks 1, 2, and 3. And so we need that, right? So we will pull out that value. And we also want to use that function, right? So instead of having to put all of this into copy and paste it again, right? We can just sort of put it into its own variable. And so let's plot our simulation. So time plot here, linearly spaced, and we'll go within the confines of our simulation, our times that were set for our solve IVP, right? And let's say I wanted 100 points. Now I also need the y values, the corresponding y values, right? And like I showed earlier, within solve IVP, there are listed as 3 different arrays. And so we need to unpack that from the solution. Since we know they will come back as 3 different arrays, we can unpack it ahead of time. And that is now taken care of. And we can make our subplots for the simulation. Subplots, cool. Subplots. All right, so I will just hard code and superimpose all 3 onto one plot here. And so x equals our times for our plotting purposes. Y equals the heights of the first tank that we get from our solution. Mode, we want it to be lines, right? And I will name it tank 1 because this is what this represents the dynamics within tank 1. And all other lines of code will match that. Instead, this will be H2, this will be H3, and this will be tank 2, and this will be tank 3, obviously. And let's plot that. And here we have our simulation of the 3 tanks that are interacting with each other for 50 seconds. And as you can see, the time that I have set doesn't quite reach uh, where they end up as in steady state. So the way I have set it up, I would have to just adjust this TN, right, to be longer. And the simulation then would then account for that. And here we can kind of see that it does sort of end up being steady state. Would have to run it a little bit longer, but you can see how convenient that is. And in any case, this is also a control problem, right? We had set up a control to where we would adjust our flow rate in so that our tank in 3 would reach a certain height. And I'll set it 4. And as you can see, it doesn't quite reach there, only being 2.4. And that is partially because we are using a really bad controller for this type of thing. But also, if we wanted to, if we were only limited to that controller, we could just simply adjust our KC value up here to maybe increase it, right? And see how that sort of, how that works within our simulation. So then we can apply it to real life situations. And with that, that is part 2 done. So thank you for watching.